Physicists say we live in a black hole, not metaphorically, not emotionally, and not just during tax season, but literally inside a black hole.
What would it mean anyway for us to be inside a black hole? How would that work?
So space has become time, and time has become space. So what you thought of as an infinitely end place in space, it becomes something that's in the future. It's like saying, I want to escape tomorrow. You go, I can't run away from tomorrow, it's in the future. That's what this thing behaves like, the singularity.
Our universe is the only universe, because all these child universes in black holes, and all the black holes have not formed yet. But when we decide to go, pick some black hole and go there, then we will realize that actually we can cross the event horizon, because now we are using different time. Now we are using the time which is there, not on Earth.
Do you think it's possible, if you're a theoretical physicist, that, like, it's easy to fall off the cliff and descend into madness?
I think that living objects are actually huge.
Matches right on with what you'd get for a black hole this size. That's intriguing. Maybe it's just a coincidence?
Then the line between the white hole and the black hole becomes unclear. They could be the same object.
Literally inside a black hole.
Like, there's some of the biggest structures in the universe.
If you run the mathematics of Einstein's general theory of relativity into a black hole, it turns out a whole new space-time opens up on the other side.
Most black holes we know of course, are much larger than this, with masses that are billions, tens of billions of times that of the sun, and with volumes that would encompass our entire solar system. What about the observable universe? We know that the universe is expanding, but expanding into what?
We're misrepresenting it when we draw it, but we're misrepresenting it in a way that we deeply understand.
Perhaps the most successful theory ever about anything fails in its attempt to predict the amount of dark energy in the universe.
Yeah.
And it fails badly by a factor of a Google.
Wow, by a factor bigger than a Google. It's like 10 to 123 or something.
Google is 10 to the 100th?
Yeah.
It gets the wrong answer by the biggest amount ever in a mismatch between theory and observation.
In the mathematics, if you put a little graphic up, you'll see it becomes something that's in the future. Mm. It's in the future. So space has become time, and time has become space. Mm. It's in the future. The future. Really beautiful. So that's the Einsteinian description of a black hole. Really beautiful.
But expanding into what?
The future. Really beautiful.
Or misrepresenting it in a way that we deeply understand.
When these types, the cosmologists, the celebrity physicists, when they're talking about general relativity, it's like they can't help but reveal that they misunderstand it. It's like they can repeat all of the principles and proposals and everything, like they know all the rules and everything, but then they don't apply those principles and rules to all situations. The name relativity says it all. That's why it's such an amazing theory. It's all in the name. One of the things that has been making the rounds here lately is this idea that the universe is inside of a black hole, or that the universe is a black hole. Well, no, the universe is not, or is not inside a black hole. I mean, it sounds kind of cool, and I suppose it's a step in the right direction. But the truth is that these people just do not understand general relativity. They're confused by expanding space and all of that nonsense that is tossed onto them by the Big Bang Theory. Gravitational potential is an observer-dependent phenomenon. This means the potential for a given region depends on the observer's relationship to the distribution of the mass and energy in that region. Gravitational potential is also what determines if an object is a black hole or not. So typically, gravitational potential is found by multiplying the gravitational constant by the mass of the object, and then dividing that by the radius of the object. But that's just an approximation. The truth is, there is no such thing as enclosed mass. In other words, there's no clear boundary. There's no place to define one chunk of mass and another. We don't know how to define the radius r. Objects, all objects, like just the idea of an object is human created. It's a human created convention. It's an abstract thing. There's no clear boundaries. Everything is part of the whole universe. The Earth has an atmosphere. So that atmosphere contributes to the gravitational acceleration on the surface of Earth. Stars are embedded in galaxies. Galaxies are embedded in clusters, and so on. The universe is just not empty. Mass and energy are ubiquitous. They permeate every nook and cranny throughout all of existence. They're quantum fields and gravitational and radiation energy. It's just everywhere. So, how do you know where to stop R so you can find a potential for a given area? Well, it depends on the observer's location relative to whatever region you're talking about and the distribution of mass throughout that region and the context of which you needed to understand it. Context is extremely, extremely important in relativity. All models and equations are just approximations. That's what they all are. It's because that we are left up to define the parameters and the formulation based on whatever physical assumptions we want to make. In general relativity, the universe is all one big giant manifold. If a black hole is defined as an object with a gravitational potential equal to c squared divided by 2, then any object, and this is the important part, any object can be considered a black hole for some observer. This is because the universe is not empty. So as you increase the distance between the emitter and the observer, and you inevitably have to include more mass. And thus the potential increases. So all you have to do is increase the distance between the emitter and the observer until there's enough mass to create a black hole. But this is not a real black hole. This is a coordinate singularity. It only exists because of the choice of coordinates. It's not a real black hole. A black hole is an object with a potential equal to c squared divided by 2 in all coordinate locations. So no matter what choice of coordinates you choose, the gravitational potential is c squared divided by 2. But what I'm describing here, where all objects can be considered as a black hole, it's not that they're a black hole, it's that they're a mathematical singularity because it only exists in some coordinate choices. There's a fundamental difference between the two. The universe is not a black hole, nor is it inside of a black hole. It is a coordinate singularity. That's because what cosmologists call the universe is something that they're modeling with general relativity, and it's a large scale choice of coordinates. So if you're talking about starlight, the emitting star would be in the center of this metric, and the metric would contain enough mass to create the coordinate singularity, putting the observer at the horizon. Now, what this demonstrates is that the gravitational potential is a radial dependent phenomenon, but also that gravitational redshift is radial dependent. This is tired light. Now, of course, tired light is the tired light theory. That refers to a specific theory where light degrades as it travels across the universe. What I'm proposing here is just gravitational redshift. It only degrades because of the choice of coordinates. You can easily fulfill the conservation of energy because that same choice of coordinates also includes a gravitational blue shift. Let's step back for a second, though. So, in general relativity, you, the physicist, you must choose the setup. This means you choose the boundaries, you choose the coordinates, you choose the mass and energy content, and if your choice is the entire universe, if that's what you want to choose as your coordinates, you want to model the entire universe, then it's going to look like a black hole. That's why everyone thinks the universe, that's why everyone thinks that Einstein's universe collapses without a cosmological constant. It's because that's what gravity does. Gravity is attractive. Of course, if your choice of coordinates includes the entire universe, it's going to collapse under perturbations. But that is important. You do have to introduce those perturbations before it collapses, which negates the initial setup anyways. So, of course, it's going to collapse. I mean, it doesn't mean the universe is collapsing or expanding. And it doesn't mean that you should add new physical phenomenon to your equations like the cosmological constant or dark energy. It just means your choice of coordinates includes a lot of mass. One thing that we can deduce from all of this is that when you're looking right at a star and you analyze the null geodesics from that starlight, and we assume that there is a symmetrical distribution of mass between you and that star, meaning all the mass of that volume of space having radius r would contribute to the total observed potential of that star, aka Birkhoff's theorem, then we can find a pattern in the gravitational redshift over large scale distances. This gravitational redshift can easily be aligned with Hubble's law, eliminating the need for expansion. Now, for a Hubble constant of 72 kilometers per second per megaparsec, the horizon that it creates is around 13.5 billion light years, which, interestingly, is also the Schwarzschild radius for that amount of mass, for the amount of mass contained within that region. That doesn't mean it's a black hole, but it also doesn't mean that that's not it definitely means that it's not a coincidence. Or it's definitely not a coincidence. It's a coordinate singularity. It's a mathematical artifact. It comes from your choice of coordinates. In other words, you're placing that star in the center of the metric and the observer at the horizon. And there's that there's enough mass to create the singularity. It is misleading and inaccurate to call it a black hole. So I've been working on this cosmological model for over a decade now. My videos get less accurate the further back you go, and I've even deleted some. But I'm always describing the same phenomenon. This idea that gravitational redshift is radial dependent. And that's because there's mass throughout the entire universe. I believe this is the correct view that cosmology should take in general relativity. All of my uploads show the journey of my understanding of this perspective and how it has evolved over the years. In the past year or so, though, I have made significant progress. I mean, it's heavy material, and I'm a terrible communicator. And I'm not even good at math and physics. And what's hilarious is that I absolutely despise making videos. But the model is parsimonious, elegant, and comprehensive. It's convincing and thorough. I mean, it deserves the attention and review of others, I believe. I've been unsuccessful in publishing so far. While I'm not just on the right track here, I have the key, and I know it. It's the golden ticket. It's not fake. I'm very likely wrong about some things, about some phrasing and formulations, minor details, but this is it. The thing that makes me so confident about it all is that it's built using existing physics. In fact, it trims the fat of physics. It just all boils down to space-time is an abstract mathematical concept. The vacuum should not be given ontological status as a physical substance. And that's because the definition of the vacuum is the absence of mass and energy. That is the very definition of it. An absolute vacuum cannot even exist. Mass and energy are ubiquitous throughout the entire universe. Every nook and cranny is comprised of quantum fields. This means gravitational potential is radially dependent, which means gravitational redshift and its respective blue shift is also radially dependent. In order to align this gravitational redshift with Hubble's law, all you need is a profile equaling rho of r equals 3 times k divided by 2r, where k is a coupling constant, which is approximately 0.833 kilograms per meter squared. It's a 1 over r relationship. The surface density of the horizon it creates is exactly 1/2 of the coupling constant k. This is remarkable. This gravitational redshift produces a cosmological horizon at around 13.5 billion light years. Near the horizon, very close to the edge of the horizon, the geometry is so extreme that it produces Hawking radiation, but the temperature is only around 1.4 times 10 to the negative 30 degrees Kelvin. So this is far too cold to be observable. But this radiation is not starlight. If you follow the null geodesics of this light in our geometry, then it follows the corresponding blue shift. which is exactly enough to bring the temperature to 2.725 degrees Kelvin that's observed in the cosmic microwave background radiation. So in this model, the cosmological constant is just the distribution of mass and energy. Dark energy is no longer necessary. Dark matter is not even necessary. This model produces rising curves in galaxies. The vacuum energy density is, again, it's just the distribution of matter and energy. It should be treated as something that is scale dependent. This model also provides cutoffs to both UV and IR light within the framework of general relativity. Now, what this means is that we can renormalize the framework using Einstein-Hilbert action. All of this stems entirely from the core proposals in quantum field theory and general relativity. Nothing new is added. In fact, it's only a minor tweak in the understanding of the relationships in quantum fields, mass and energy, and space-time. I kind of think that the best way to understand this is to remove the physical status of space-time. So if space-time isn't real, then matter and energy permeate all locations. And they're not, it's not that space-time is a basket, because the basket is matter and energy as well. So space-time is just an abstract human thing that we assign, it's properties that we assign to the basket. But the basket is still made of mass and energy. If you do this, then all of the consequences of everything I've discussed follow. And physics can be completed. But, these people are stubborn, so I don't know what to do. Make YouTube videos. Thanks for watching. Y'all have a great day.